We're getting near the end of the semester, and so you may find me spending a little more time at the beginning of class discussing issues of general interest to everybody. We're now doing relativity, the theory of relativity, and I made a very special decision that I know how hard it is to learn relativity. And you ask me questions, I give you answers, and your response is, huh? And that's the way it should be, because it's a subtle, difficult subject. If nothing else, what I hope you're learning is that it's a subtle, difficult subject. I want you to, based on your asking me questions and the utter confidence in which I give answers, to get the sense that there are no real contradictions here, but there are lots of places where you can confuse yourself and think there are contradictions when it turns out there aren't. I'm not giving you enough time or math for you to be able to feel comfortable with this. Let me just assure you that very few people who major in physics or even get their PhDs in physics have the same comfort with relativity theory I have. That's simply because I spent a lot of time teaching it, getting into it, understanding it, and writing papers on the subject. But there are no contradictions here. It gives a different way of understanding time and space that is very thrilling. And I'm exposing you to this, but I don't expect you to master it based on the 2 or 3 lectures that we have on the subject. As a result, I will not put an essay on relativity on the final exam. So you can sit back and relax. Now, there may be multiple choice questions, you know, about Lorentz contraction or something like that. And so you have to know this relativity. But I'm not going to ask you to explain in your own compelling, convincing words why a train being stuck in a tunnel can be, how you can explain the paradox that it seems to be inside the tunnel in one reference frame, but it's never totally inside the tunnel in the other reference frame. I'm not going to ask you to do things like that. And that's because we're not spending adequate time on it for you to be comfortable. You know, on earthquakes, I think you can do that. On energy gaps, you could do that, but relativity is too abstract, too difficult. What I want you to get out of this is a sense of what relativity is talking about, the understanding that there are no contradictions here, that it affects time and space, and to be able to answer multiple choice questions on it. So, no relativity essay on the final exam. The final exam is coming up in about 3 weeks, less than 3 weeks. We're going to arrange a review session before the final exam. A lot of you went to the review session before the midterm. It was a very, feedback I get is that people there felt it was great. So I recommend that you all go. The final exam will consist, as I discussed it with GSIs yesterday, because there's limited time we have to grade this, we will only have one, you will answer 1 out of 3 essays. We'll give you 3 essays you get to pick. It's a long course, and so rather than just pick 2, you get a choice of 1 out of 3. The essays will be about the same length as on the midterms. This has more to do with our limitation of getting your grade in than anything else. There also will be multiple choice questions. Instead of 20, there will be 40 multiple choice questions. They will cover the entire course. They don't emphasize the end of the course, the middle of the course, or the beginning of the course. I do not claim that they will be absolutely equally distributed. I'm not going to try to emphasize anything, but if I come up with good questions, I'm not going to make sure that every chapter has the same number of questions. So that's what I'm saying about the final exam. It is coming up in less than 3 weeks. So be alert to that. We have, after this lecture, there are only 3 more lectures. We will be going, we probably won't start today, but certainly on Tuesday, we will get into the universe chapter. There may be something in the universe chapter on the final exam that's not as abstract and difficult as relativity is. We're talking here about facts about what's out there in space. I haven't decided yet because I don't know what the questions are. But that reading for that will be due next Thursday. That's the last chapter of reading that is due. I got an email from Black Lightning Notes. They're looking for someone. They would like to have a note taker in this course next semester. Their usual rule is they will only take your application if you get an A in the course. Then they'll want you to submit typical notes. If they hire you, then you will take notes next semester. They probably require you to actually be here in the classroom rather than on the webcast. And they pay $35 per lecture. So that's not a bad job, $70 a week, for taking notes in a course in which you already got an A. But if you are interested in this, then here's the person's name is Karen Austin, and you can email her at Karen, Karyn, @berkeley.edu, or you can go to the Black Lightning webpage and fill out a form there. So I've had really good experiences with Black Lightning notes in the past. Many of you feel, why bother? You're here. But sometimes I say things in class that a good note taker will notice. Like whenever I say, and pay attention to this, it may be on the exam. I actually say that quite frequently, you'll notice. And then some of you don't notice, and then it's on the exam, and you say, but this wasn't emphasized in the text. And we've gotten some comments like that. But many of those questions were things that I specifically emphasized in class were important for you to know. So it is important. The lectures are important, especially for questions of emphasis. So onward with a little bit of general relativity. And I want to talk about forces. And we're going to be bringing relativity and quantum mechanics together in today's lecture. Any questions on relativity, things that have been bothering you, things we discussed last time that have your head swimming and seem to make no sense, even though I insist they do? Here's a chance. You can do it before class, or you can do it right now. So I scan. I don't see any arms up. That's... Yes? He says he doesn't understand tachyons gain energy by slowing down. Energy is equal to gamma m naught c squared. That's true for tachyons. That's equal to 1 over the square root of 1 minus v squared over c squared times m naught c squared. Now, v is larger than c, so this number is bigger than 1. So this number is imaginary. So let's write this. This is an answer to the question. You don't have to know this algebra. Okay? So let me write it as 1 over the square root of minus 1 times the square root of v squared over c squared minus 1. Now this square root is always positive because that's bigger than 1, so it's a big number minus 1. So that all works. And I leave in the m naught c squared. Okay? Now we have this thing here. That's the imaginary number I. And energy isn't imaginary. Energy is real. Ah, well, this must be imaginary for a tachyon. So it's I times m of the tachyon. Okay, so now the i's cancel. And we get that the energy is equal to m naught c squared over, so this is the formula. This is m tachyon, rather, t squared, over the square root of v squared over c squared minus 1. So there's the equation for the energy of the tachyon. Now take a look. Suppose v is infinite. Then this number is huge. Subtract 1, hardly notices. You're dividing by a huge number. The energy is 0 when the velocity goes to infinity. 0 when it's really super fast. Suppose it's going at the speed of light. If it's going at the speed of light, v equals c, and this is 1. 1 minus 1 is 0. Any number divided by 0 is infinite, so it has infinite energy when it's going at the speed of light and 0 energy when it's going infinitely fast. That's the funny behavior of the tachyon. You got to know this? Nah. Any other questions? On the other hand, you may have fun knowing this. You know, you want to tell people about tachyons. You have to know that tachyons go faster than the speed of light. Yes? Okay, the question is relativity just a theory? It's just a theory like all of physics is just a theory. Okay, in other words, relativity is a theory in the same sense that electromagnetism is a theory, in the same way that the theory of gravity tells us how to put satellites in orbit. It's on an equal foundation. We have no experiments that contradict it. Other theories that don't include it are easily proven wrong by experiment. So it's a theory in the sense that it provides an explanation for observed things that no other theory can provide explanations for. That's the best we do for any physics theory. So when you say it's just a theory, that's like saying, are numbers just theoretical? Or is biology just a theory? Relativity is a theory, as a theory, is probably better established than evolution. Okay. Let's have a quiz. Get out your quiz page. Okay, are we ready? Got your quiz sheets out? If not, did you forget to bring one? Buy one quickly. For those of you who are selling extra quiz sheets, the going price is actually pretty high these days. You can really extort a lot. Okay, time to stop looking at your neighbor. Time to stop talking. I want no blinking because I understand some students have been putting notes on the inside of their eyelids. So no blinking. If you blink, we will notice. We have cameras up here recording you. No blinking. Are you ready? Here's the quiz. I think it's quiz number 9 if I counted right. Here are the questions. In fact, I can zoom in. Okay, first question, time. We know time is affected by velocity. That's what we've been talking about. But it's also affected by other things too. Actually, or is it? None of the above? Okay, so the question is it affected by anything other than velocity? Is it affected by gravity? Time slow down when you feel gravity or speed up or something? Is it affected by electricity when you have time in an electric field? Does that affect it? Is it affected by magnetism? Here's a clue. Or is it affected by none of those? Here's a clue. The chapter actually addresses this question. That's why it's a test, right? The chapter either says, oh, it's not really affected by anything explicitly saying that, or it explicitly says that it's affected by one of those things above. So if you read the chapter, you should get the answer to that. So A, gravity, B, electricity, C, magnetism, and D, none of the above. Question number 2. Could time stop? Well, again, I'm interested in what I say in the chapter. It's really a test to see whether you read the chapter. I say something explicitly in that chapter. In that chapter, I say, yes, but as far as we know, only in a black hole does time stop. B, no, time will go on forever in the universe. C, yes, time does stop, but only for tachyons. Or D, I don't know. I don't know. Okay, question 2, could time stop? Yes, but only in a black hole. No, it will go on forever. C, yes, but only for tachyons. D, Muller doesn't know. You may know, but the question is whether I know. Okay, pass in your quizzes. Someone said do that again, so I take it like that. Okay. Where did what go? Oh, someone asked, where did the chalk go? It went into a black hole. What? You didn't read the chapter. You didn't see the part about black holes? Okay. 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 It should all be passed to the aisle now. If you haven't handed it in, panic. Let's go on. There was an interesting aspect that we discussed last time, that energy of a moving object. We're so used to it having energy. After all, a moving object has energy. And now we're saying that you can express this, instead of expressing it as in the velocity, you can express it as being in the mass, because moving objects have more mass. As you get them going faster and faster, they store more and more energy. As it approaches the speed of light, the energy, which is gamma m naught c squared, or just mc squared, the gamma goes to infinity. So as you get near the speed of light, the energy is infinite. That means it takes infinite energy to get something up to the speed of light, which we can't achieve. There's no way we can harness infinite energy to do anything. So no object that has a rest mass could possibly go at the speed of light. And as I discussed last time, no object that goes at the speed of light could go slower and still have any energy left. But this is a curious thing, because the mass is increasing, and yet mass is the essence of gravity. And so you ask yourself, as this thing goes faster and faster, does it really weigh more? Does it get heavier? And this has been tested in the laboratory. The answer is yes, this is really a mass increase. It really gets heavier. There's a stronger pull of gravity on the object as it's going fast because of the fact that it has more mass. So here's an interesting connection now between gravity and energy. This really intrigued Einstein, that gravity, maybe gravity should be brought into this in some way. He finally did that. It was hard. It took him 11 years to finally get it all straight. He had to invent a lot of new mathematics to do it, very difficult math. And his theory of relativity, the original theory of relativity, was published in 1905. Later, his theory of gravity, which was given the name by him of general relativity. Theory of general relativity it has a confusing name. I mean, the theory of relativity was really about space and time. The theory of general relativity was also about space and time. But what it did was include in gravity. So I want you to know this, that the theory of general relativity is really a theory of how gravity relates to space and time. It's really a theory of gravity. And back in 1916, when he did this, there were different forces that were known. Gravity was, of course, the most fundamental force of all. We've known about that ever since humans could think. Gravity is, they used to say, it's the natural tendency of things to move in the downward direction. That doesn't explain a thing. Newton recognized that gravity was the force of attraction between the Earth and you. And his great breakthrough was to realize the same force of attraction works between the Earth and the Moon, and that's what keeps the Moon going in a circle. So suddenly, the motions of the Moon and your own feeling of weight were all part of the same thing. It was the first great so-called unification of the forces. Go back before Newton, and there's the heavens. They do their thing, and here we are, and we fall. But they weren't seen as being related. When Newton realized that they were related, suddenly two things that seemed to have no relationship with each other, the motion of the Moon and the motion of the chalk, were actually two aspects of the same thing. That's called the unification of the forces of physics. It was no longer the motion of the heavens and the motion down here on Earth. It was all the same thing. This idea that two different things you see could actually be two aspects of the same thing has been really a driving idea in physics ever since. Now, there are other forces. We talked about the electric force. Electric force is kind of strange. There's an electric force between two objects only if they have a charge. And so you have two electrons that will repel each other. But if you have an electron and a neutron, they just sit there. There's no force. That's kind of weird when you think about it. I mean, everything falls, right? In fact, all things fall at the same rate. You get a big heavy thing and a little light thing, and they fall together at the same rate. How could that be? Why? It's not obvious that they do. Galileo had to demonstrate it with an experiment that some people think was actually done at the Leaning Tower of Pisa. But it's not really obvious that a heavy thing would fall. Why does a heavier thing fall no faster? Well, the reason is it's harder to get a heavy thing going. Right? This is heavy and has a big force on it, but you need a big force to accelerate a heavy thing. Whereas a light thing doesn't have much of a force, but you don't need much of a force to accelerate this, so they fall together. It's an interesting cancellation that takes place. This is the force of gravity, but the force of electricity, a force on a proton and an electron, they're in opposite directions. You have an electric force, and the proton will be attracted, and the electron will be repelled. We have something here, something in a box. I won't tell you what it is, but there's something in there. And outside, there's an electric field. And you put a proton here, and it's attracted. And you put an electron here, and it's repelled. And the forces are equal and opposite. What's going on? Well, what I have in here actually is another electron. Didn't tell you that. But this creates an electric field, and this particle is repelled by it, this one's attracted. Gravity's different. Gravity is always an attraction. Well, what about anti-gravity? Well, it doesn't seem to exist. What about this recent discovery of the acceleration of the universe? We'll get to that. It's not really anti-gravity. People use the term anti-gravity for that just to make good newspaper headlines. It's not really anti-gravity. All things seem to be attracted by gravity. It's rather strange. But with electricity, it's not. So, this seems to be a different kind of force. Magnetism and electricity aren't really that different. If you don't have an electric charge, you won't feel any magnetism, and you won't feel any electric forces. The electric charge is the same for both. Magnetism and electricity, as I discussed, seem to be two different aspects of the same force. One of them that depends on velocity, and the other depends on just sitting there. But there are things like neutrons that just sit here, and they don't feel the electric force at all. There are other things like neutrinos. Here's the symbol for a neutrino. Little Greek letter for the N. Eta, I guess it's called. Nu. It's a nu. N-U. The Greek letter for the neutrino. It doesn't feel the electric force at all. Now, electric forces are very important. Electric forces are what hold the table together. Atoms sharing electrons. They're what hold you together. And then to get there, these particles don't feel them. There's the neutron that's inside the nucleus. What holds that in there? Why doesn't it just sort of drift away? It's not held in by gravity. The force isn't big enough. Why doesn't it just fall out? What holds two protons together in the nucleus when they're repelling each other? Well, before it was really understood, people said there must be another force. We'll call it the nuclear force. So we had gravity. We have E and M, electricity and magnetism. We have this mysterious nuclear force that holds a nucleus together. These were the forces that were known at the time of Einstein. Einstein was particularly concerned with gravity because of the fact that it seems to act on everything. And his sense was, if mass is energy, then what maybe gravity is operating on is the energy. That it's the energy that makes this has energy, therefore they attract each other. And he started thinking about this and trying to make sense out of it. And it took him 11 years. And he came up with his theory of general relativity. So here we go with another abstraction. And no, there will not be an essay on general relativity on the final exam. So relax a little bit. Let your mind loose. Let it go. There is no possible reason I can think of why a future president needs to know what I'm about to tell you. There may be a multiple choice question on the exam, so don't fall asleep. It's all in the text, however. So here is the idea of general relativity. And it comes out of Einstein's insights that space is funny. Remember I talked about going to Sirius? I looked it up. It's 8.3 light years away. Okay? If you're going to Sirius and you say, oh, it's 8.3 light years away, boy, it'll take me a long time to get there. And then you speed up till you're going near the speed of light, and so your gamma is 7, or let's say it's 8.3, you go a little bit faster. And then in this reference frame, you say, well, fortunately, in this reference frame, it's not that far away. A moment ago, when I was doing things in the lab rest frame, it was 8.3 light years away. Now, I am traveling at a gamma of 8.3, and in this frame of reference, Sirius is only 1 light year away. By the way, Sirius didn't move. The distance between me and Sirius didn't change. All that's happening was a moment ago, I was more interested in the lab frame of reference, and now I'm more interested in my co-moving frame of reference. If this is confusing you, don't worry about it. There's not going to be an essay. Just listen to me talk and see, try to take in the way I approach problems on relativity things. So the distance between me and Sirius didn't change. It always was 1 light year in a frame moving with a gamma of 8.3. It always was, even before I started moving with 8.3. In that reference frame, it always was that close. In that reference frame, that's my co-moving frame. That's the frame that will determine, I will spend a year, and I'll be a year older in that reference frame, and then I'll be at Sirius. But think of it. The distance between Sirius is fairly much undetermined. There's a flexibility to space. The time between two events depends on the reference frame, depends on their paths. Einstein decided to see what he could do because he thought this could solve the problem of gravity. And it came out in a very strange way that is harder to understand than everything we've done in relativity so far. Einstein was able to write down an equation. It's actually a relatively simple equation. The equation looks like this. It says that a big thing called G, well, let me use the letter R. That would be better here. R is a complicated mathematical object that tells you about the distortion of space and time. It's actually a collection of 16 numbers. Let's not get into the details. This is the theory of general relativity, that this distortion of space and time is equal to a constant, which is the gravitational constant, that's why I'm saving G, times a number that basically represents the energy of the object. This was his equation. Now this is 16 different numbers. It turns out it's in a collection called a matrix or a tensor. And the energy is not just the total energy, it's actually the energy momentum density. And that's also a complicated object of 16 things, and it's different everywhere in space. So the equation is simple, but the math behind it is complicated. He basically said the geometry of space and time depends on the energy density. Energy density being a four-dimensional density of a four-dimensional energy. If you understand those words, you're the next Einstein. A simple equation. What he was doing is saying space and time are distorted by energy. Before we said they depend on your velocity. He was saying now they depend on energy. This comes about from the fact that energy and mass are related, that in Newtonian theory, the gravity comes from mass. Now we're saying it's not really the mass, it's really the energy. And what gravity really is a distortion of space and time. So sometimes I'll draw a little diagram that's often used to give an analogy of what happens here. Suppose you have two objects, or you have an object like this, two bullets, and they're moving through space like this. And here's a very massive object. This may be the sun. And the bullets may be light. And the experiment was first done with light passing close to the sun. What will happen? Now, from Newtonian theory, you'd say nothing. Light has no rest mass. According to Einstein, if light has energy, then it has mass. It may have no rest mass, but the energy is equal to gamma m naught c squared. This may be 0, but this is infinite. And so, yes, you could have energy. In fact, it turns out to be HF. So these things do have energy, even though they don't have rest mass. And because they have energy, they feel gravity. You see, gravity of the forces comes about from energy. E and M comes about from charge. If you don't have a charge, you don't feel the electromagnetism. You just ignore it. The neutron just sits there. It doesn't even know there's an electric field there. It doesn't have any charge. For the nuclear force, there's something called a nuclear charge. And you can only tell if something has a nuclear charge by putting it close to a proton and see if there's an attraction or a neutron or something else that has these things. So here we have the two photons, and they're coming near the sun. And although they don't have rest mass, they do have energy, and therefore they have mass. They have gamma m naught, even though they don't have an m naught. You might call this the kinetic mass, the mass of motion. And because they have mass of motion, they feel gravity. So even light should feel gravity. And as a result, and gravity is always attractive, at least in general relativity theory it is. And general relativity theory seems to explain everything we know about gravity, even the acceleration, the sort of thing that the newspapers call anti-gravity, even that fits into general relativity in a very simple way. In fact, Einstein originally predicted that there would be there would be an acceleration of the universe. But he withdrew that prediction because he thought it contradicted facts. It was a great mistake he made. Something called the cosmological constant that pulls in there and would have predicted the acceleration of the universe if he had left it there. So these two photons come, and as a result, they're pulled in, and they will be deflected like this. Now, the experiment was first done in 1921. Hard to see starlight when it's going right past the sun, so the experiment was done during an eclipse of the sun, when the moon was between us and the sun. So here we are. Here's the moon blocking out the sun. And then you look at stars, and the light is coming from a slightly different direction. You see, it looks like it's coming from over here. And this light looks like it's coming from over here. So, because of the deflection, this is called gravitational lensing. And you will read about that if you look it up. You can look it up. Gravitational lens. A lens bends light. Well, so does gravity. Look that up on the web if you're interested. You'll find there's a huge field of people looking at massive objects other than the sun by the amount they bend light. But it was first done around 1919, 1920, when there was an eclipse of the sun. I don't remember the exact year. And people looked at these stars, and they were a certain distance apart. And then the sun got in between, and they appeared to be further apart. Because the light was deflected inward, and because it was coming in at an angle, it looked like it was coming from further apart stars. And this was a big thing. It made Einstein into the most famous scientist in the world overnight, because he had made this prediction. The change is very small. You could barely see it. You need very precise instruments to see it, but it turned out to be exactly what he predicted. So that was a great event in the theory of general relativity. And someone just said, how many people in the world understand general relativity? And it wasn't Einstein, but someone else said, about 6 people in the... This is a number I heard when I was growing up, that there were only 6 people in the world who understood general relativity. Einstein might have given a different answer. He might have said nobody. Or he might have said, well, there are hundreds. But somebody, I think because somebody was one of the people who understood it, wanted the number to sound really, really small. That made him look super, super special. And so he said 6, and that number has sort of come down through history. It's ridiculous. I mean, there are thousands, there are tens of thousands of people who understand general relativity. I understand general relativity. It's not such a big deal. We have an undergraduate course in general relativity that physics majors take. They learn that stuff instead of learning, about Priuses and nuclear weapons and communication theory and invisible light. That's what they learn. They like to learn general relativity. That way they could be one of the 6. It's really a very prestigious thing to do. So, so this was the experiment that was done, and it verified what he said, and it shows that light is deflected. But now, why did Einstein come up with this prediction? The way Einstein explained it is really quite remarkable. And you can understand it in terms, what general relativity did was it said that according to that equation right up there, space and time are changed when you're close to a clump of energy. Now, this is basically an analogy, but it's a correct analogy. It really shows you the essence of what's going on. Imagine that you have 2 balls rolling along this table, and they'll go in a straight line. Now you put an object here that distorts the shape of the table. In fact, imagine that it's sort of hollowed out. So there's a hole here. That's analogous to the change in shape of space and time that takes place in general relativity theory. It's only an analogy, but it's a pretty good one. Now these things are coming along, and suddenly they're feeling themselves inside of a hole. Let me try to draw that here. So here's the top of the table, and these things are coming along, but here there's a hole. And I can't really draw that very well. Maybe that's not an even bad way to draw it. Just think, here's a region that goes down. The space is distorted by the object of this mass. And so think of that as a hole going down. And this thing comes in, and now you're going along a hole, and it's like a tilted racetrack. If you don't turn your wheels, but you're on a tilted racetrack, you will go around the racetrack a little bit, like that. And over here, if you don't turn your wheel, you just go straight. But you're inside of a bowl. You know, spin a marble inside of a bowl, and it goes around. So this one gets deflected this way. And what's really happening is the particles aren't feeling any force. What happens is they're going in straight lines through a curved space. So according to Einstein's general relativity, the presence of energy, mass, but energy density, that's actually the 4-dimensional density of the energy momentum tensor, distorts the local space and also the local time. And so a particle going in a straight line, the straight line will be like this. Will turn. Because that's what's straight. Straight means you follow your nose. You follow your nose around a tilted bowl, and you'll just go straight. You know, I could take a piece of paper and draw a straight line on it. There's the straight line. Now, if this is curved, then I'm following the straight line. I can turn it into a cone. And if I turn it into a cone, you know, it'll come in at this angle and then go out over there. It's still going in a straight line. It's following its nose. It's not feeling any force. It's not turning in any way. It's the space that's turning. So this is the general relativity. Rather amazing concept. The fact that the math works out is something you have to trust me on. But it really does. It's a distortion of space and time by the gravity field. That's the answer to one of the quizzes. Yes, quiz questions. Yes, space and time are affected by gravity, not by electromagnetism. Now, there are other simple cases that we can talk about. This one is perhaps even more mystifying than what I just said. There are a lot of people who like this, live with it, find it kind of interesting. But the one that I'm going to tell you right now will bother a lot of people. And that's the following. If I drop 2 objects, boom, they fall. They have a force on them. Well, that's old Newton theory. In relativity theory, they have no force on them. No force whatsoever. What's going on? Why are they falling down then? Well, they're not. They're moving in straight lines. Why are they moving at all? Well, they always were moving. I mean, here we are. The Earth is moving. They are moving. We're moving at 30 kilometers per second. We're moving together. But because as we move together, the space around the Earth is distorted, they wind up curving towards the Earth through this distortion in space and time. if they're moving at exactly the same velocity, which these are, and we're all moving together at exactly the same velocity, they will all curve the same amount. That's why they fall at the same rate. They're going through the same curvature of space and time. And so what Einstein did, in a sense here, was to take the theory of gravity and give a different justification. This is no longer separate from relativity. It just takes the fact that mass is energy, that energy is a distortion of space, and all of gravity is a distortion of space like that. Time is a particularly interesting one. Einstein came up with this elevator analogy. This was an analogy for the light passing the sun. Let me give you an analogy for time. You can see why I'm not going to ask you to write an essay on this stuff. We're covering a lot of very abstract material very quickly. I'm trying to give you the flavor of it. We do the same thing for the physics majors when they study this stuff. The only difference is they spend a little bit more time learning how to calculate it. They don't understand it any better. We teach them how to do some elementary calculations. One of those is the effect on time. So Einstein came up with this elevator analogy. According to relativity theory, you could be on the Earth. Here's the Earth. And you put yourself in a box. And here you are sitting in this box, and, okay, I feel gravity. He said, but gravity is a distortion of space and time. You want to understand this, consider a second box over here, far away from the Earth. And this second box is part of a rocket ship. And it's being blasted upward. It's accelerating at a constant rate. Now, we didn't talk too much about this when we did gravity, but when I drop these two objects, they accelerate. It's as if their foot is on the accelerator pedal, and they're picking up the same amount of velocity every second. It's 9.8 meters per second they pick up every second. This is called the acceleration of gravity. Let's call it 10 meters per second. Physics students have to learn that's 9.8, but 10 meters per second. So that means after 1 second, each particle is going 10 meters per second. After 2 seconds, they're going 20 meters per second. They're accelerating at that rate. It's like accelerating a car. And if you were to accelerate a car this much, if you have a super car and step on the gas pedal, so that after 1 second, you're going 10 meters per second, after 2 seconds, you're going 20, you will feel a force pulling you back. It'll feel like a force. Pulling you back, it'll be equal to your weight. Yes? Per second squared. No, this is, okay. Acceleration of gravity is 10 meters per second every second. In this class, I prefer not to use square seconds because some people are confused by it. Every second, you gain 10 meters per second. Okay. What Einstein said is, here you are on the ground, and here you are in a rocket that's actually accelerating, and the rocket's pushing against you. You feel this force on your feet. And the question is, how can you tell which one you're in? Can you tell if you're sitting on the Earth, or can you tell if you're in a rocket that's accelerating? What measurement can you do that would distinguish the two? And Einstein's answer is amazing. There is no experiment. These are indistinguishable. This is sometimes called the equivalence principle. And the reason they're indistinguishable is that in his mathematics, they are the same. This is coming about because the space-time is actually being accelerated by that mass. In here, your space-time is being accelerated by that rocket. But they're identical. This math is the same. You can't tell. You cannot tell if we're sitting here in this room. I mean, maybe I didn't tell you that, but the little thing when you weren't looking. Here you think we're sitting on the Earth. Well, actually, what I did is I got rid of the Earth at the beginning of the lecture. And ever since then, I put a shell around this so that the air wouldn't escape. And I put a rocket motor on the bottom. This is the greatest demo I've ever done in physics, in Physics for Future Presidents. And we are now in a rocket ship blasting off, being accelerated. And it feels the same to you because there's no way you could tell. So if you have an object like this and you let go of it, it looks like it's accelerating downward, right? But it's not. when I let go of it, it's actually not accelerating. It's moving at constant velocity. Wherever velocity it had, it isn't changing. But the whole classroom is accelerating up into it. That's general relativity. It's kind of weird because here we are, and on the other side of the Earth, they are accelerating the opposite ways, but we're not getting any further apart. But general relativity can handle that too. So this is the equivalence principle. Now, based on this equivalence principle, we can start thinking about gravity and what effects it has. And one of the interesting things is, suppose I have a clock at the top and a clock at the bottom, and this thing is accelerating together. The top is being accelerated, the bottom is being accelerated. Are they going at the same speed? It depends on your reference frame. If you send a photon down or some other way of communicating between them in order to compare the clocks, it takes some time for that to come down. By the time it reaches the bottom has accelerated more. As a result, a clock up in the high altitude will have a different rate of speed than a clock at the bottom. What do I want you to know about this? For the final exam, I just want you to know that fact. That in a gravitational speed, there is another time effect. The time effect is that clocks at high altitude will actually go faster than clocks at low altitude. If you fly in an airplane, then there are two effects. One is you're going faster, so you slow down. The other is you're at high altitude, and so you speed up. Do these effects cancel? No. But the experiment was done by two scientists named Heffley and Keating, who realized you could take really accurate clocks and actually fly them in an airplane. You could change the velocity of the airplane. You could change the altitude. You could measure all these things, see if the clocks were slowing down because they were moving, and then by going to a higher altitude, speed them up and measure all these things. They did that. It was published in Science about 30 years ago. They actually did it with one clock on the ground, one clock on the airplane, and with sufficiently accurate. It's a very small effect. In fact, I have the equation here for the size of the effect. This is it. You want to know how much time is slowing down? That's the factor. G here is the acceleration of gravity. It's 10 meters per second every second. C is the speed of light. 3 times 10 to the 8th meters per second. H is the height in meters. So if you go up a kilometer, H is 1,000. Go up 10 kilometers, H is 10,000. You plug that in here. I put in 100 meters because this experiment was actually first done in a tower on I think it was the Harvard campus. 100-meter high tower, and they actually measured the time change. And you look at it, and you put in the numbers and put in C, and you get the gamma is 1 plus 10 to the minus 14. I mean, gamma is pretty close to 1. It's 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's the gamma. It's amazing that you can measure that, but you can with super accurate clocks and with in this case, instruments that could measure the frequencies of gamma rays to very high precision. So it's a small effect unless you go really high. If you're in a really strong gravity field, the effect becomes huge. There's a companion to Sirius. There's a white dwarf star that is a very compact mass, has huge gravity on it, and the effect is quite large for that star because G is so big. In a black hole, this effect becomes enormous. In fact, if what you're talking about is actually going from the surface of the black hole to infinity, this effect becomes infinite. Time slows down by an infinite amount on the surface of the black hole compared to the outside, because the gravitational field is so intense. I'm throwing facts at you here. I think the way you learn this stuff is you listen to me and you're sort of overwhelmed. You're going to lose. There are just too many things that are non-intuitive for you to understand. And so you're trying to remember whether time slows down or speeds up on the surface of a black hole. You'll be really confused by that. I want you to know it changes. Turns out it slows down. we are going slower down here because of the fact that we're on the surface of the Earth than we would be if we were in space, by just a little bit, not very much, small effect. But this effect on time is an aspect of the fact that general relativity accounts for gravity as a distortion of space and time. Now, this is enough general relativity for now. Let's get to something a little bit more concrete. We said that mass is energy. And that, for example, a positron, which is an electron with a positive charge, when it hits an ordinary electron, the charges can cancel, and you're left with nothing but mass. That then can what we call annihilate. They can turn into two photons. It turns out the photons will go in equal and opposite directions. That's the consequence of what we call momentum conservation. And they come out as photons. All of the mass energy, all of the rest mass energy goes into creating these photons. When a photon hits a surface, it can disappear. It's just an electromagnetic wave hitting you. All the energy is absorbed. It warms you up a little bit, that energy, and that's basically it. This is called annihilation. And we used it in the PET scan. In the PET scan, you have a person here. Long-haired man. And you have them eat some iodine that emits positrons that goes to their thyroid. The gamma rays come out from annihilation because this thing emits positrons. The positrons find a nearby electron within a millionth of an inch, and then they annihilate, and you get two photons. They go in equal and opposite directions. The detectors now know that this came from somewhere along this line. The next one that is somewhere along this line. They get to see what part of the thyroid is active, and guess what? None of them are coming from this lower half of the thyroid, and so the PET scan knows that that part of the thyroid is not processing iodine. That's how a PET scan works. Positron emission tomography. You all know that because you studied it for the midterm. Maybe you forgot it because the midterm was last week, and you don't remember things that long. But you'll need it again for the final exam. Now you can reverse this. Suppose you take two gamma rays and bring them together. Can you make an electron and a positron? Can you reverse this? The answer is yes. And that is how we make antimatter. You can take very energetic gamma rays and essentially collide them. Usually it's done by not using gamma rays, but by using very high energy electrons. You have two electrons come together with very high energy. They bang into each other. Some of that energy can be turned into creating an electron and a positron. So this is the way it works. You have an electron plus another electron. They're brought together head-on to smash into each other. When they do that, some of their energy is used up, and you're left with two electrons. You're left with E minus and E minus, but you get out an E plus and an E minus. You're basically reversing this. You're turning energy into matter and antimatter. This is how we make antimatter. Question?
A question on the diagram you drew there.
Yeah.
Sun. Can the velocity of an object be greater than the force of the gravity, and if it is, will it still bend?
It'll always bend a little bit. An object that's going super, super fast will bend less. Now, light is different. Super, super fast, you're not going faster than light. So, massive things will bend more. But even light will bend. Everything will bend a little bit because space is curved like that. So all objects will bend at least a little bit. Light, usually the least of all because it's going so fast. Yes?
How do neutrinos react to that effect?
They bend too. Question is, what do neutrinos do? How do they respond to the curvature? They have energy. So they bend too. Has this ever been observed? Not directly, no. Neutrinos are particles that do not feel E and M. They have no charge. They do not feel the nuclear force. So they can pass right through the nucleus and not feel a thing. But they do feel gravity. Gravity is a very weak force, and generally the nucleus doesn't have enough mass to affect them. But if you have the Earth or the Sun, the neutrino can be deflected slightly by that. I don't think it's ever been observed, but there are other effects that have been observed for neutrinos. It looks like they are affected by their passage through the sun in an interesting way that maybe we'll get to. So what I want you to know is the following. The way you get antimatter is by making it. The way you make it is by taking really energetic particles and smashing them together. And if they lose enough energy to make up for the mass of a positron and an electron, then sometimes that's what happens. And the things that come out are the original particles plus a new electron that has been created out of energy plus a new positron. They always have to be created together because they have to have equal and opposite charge. You can't make charge. Charge doesn't change. You can't start with two electrons which have two negative charges and then wind up with two negative charges plus a positron. That positron charge has to be balanced by an electron charge. So you always do them in pairs, and this is called, and this is a term I want you to know, it's called pair production. Now, what I want you to know about pair production is you could produce antimatter. The fact that you could do this comes right out of relativity theory. Antimatter seemed, when Dirac was working out his relativity equations in quantum mechanics, there was this little annoying term that kept on showing up that seemed to indicate you could have an electron with the opposite charge. His reaction was, oh, that must be a proton. But now we know there is an electron with the opposite charge. It's called a positron. It comes from relativity. And you could turn energy into rest mass. You do that by having really energetic particles collide. They do pair production, which means you produce a new electron and a new anti-electron. The first antiproton ever seen was discovered here at Berkeley by Owen Chamberlain, who just passed away a few weeks ago. It's going to be a memorial service for him. I think it's this coming weekend or the next weekend. I'll check my calendar. Owen Chamberlain and Emilio Segre and Clyde Wiegand here at Berkeley discovered the first antiproton. Question?
Why don't the new positron and electron immediately annihilate?
Because they're moving away from each other. They have excess energy. The positron will go and will eventually lose its energy, slow down, and then it'll get to another electron. But when they're produced, they're usually flying away from each other with excess energy. If you produce them at rest, you just barely produce it, then they probably will annihilate with each other. Okay? So the way we get antimatter, now there may be a planet out there. We actually know that there's nothing nearby that's made out of antimatter. And the reason is, well, I can get into that. It has to do with the fact that there'd have to be a boundary between the matter and the antimatter where there's enough particles that we would see the annihilation, which we don't. Even space isn't so empty that we wouldn't see that. So there's nothing nearby that's made out of antimatter. But maybe if you go really far away, we'll find something that's made out of pure antimatter. There's an interesting issue, which we'll get to as we discuss cosmology, which is why not? Why is the world made out of antimatter, made out of matter and not antimatter? I'll give you the answer to that in just a second. Our best answer right now in just a second. But as it is today on the Earth, the only way we make antimatter is by taking huge amounts of energy and making pairs. Then we have the antimatter. We can actually store the antimatter. It's stored these days in what are called storage rings. With magnetic fields, the antimatter will go in circles for a fairly long time. You can actually store it in a little magnetic bottle and have a little positron that just sits there. People have done experiments to see whether positrons fall in gravity or are they anti-gravity. Well, Einstein predicts they would fall, and indeed they do. So they are attracted to anything that has energy. The fact that they're antimatter doesn't give them anti-gravity. There seems to be no anti-gravity whatsoever in general relativity theory. Now, see, I was going to say something about, what was I going to say? I said in a moment what I'm going to tell you about. Why is there no antimatter in the universe? Fundamental answer is we don't know. Second answer is, what have people proposed? The answer is. And there actually is a very good proposal. It's the only one that has any plausibility, and so many of us think this has a good chance of winding up to be true. I think I'll share it with you. The original Big Bang, which we will be talking about in some depth next week, the universe was created, and in that universe there was an equal amount of matter and antimatter. Now, actually it's not quite true. It was almost equal. According to this model, there was a slight excess of matter. The ratio of matter to antimatter was 1.000001 to 1. It was 1 plus 10 to the minus 7th. I don't know if I got that right. It was a tenth of a part per million extra matter over antimatter. Is that possible? It turns out to be possible according to current measurements of particle physics because of something called CP violation. It was a thing that got Fitch and Cronin a Nobel Prize, a discovery that we might talk about more next time. But it turns out in nuclear reactions, there is something called CP violation that makes it possible. It was Andrei Sakharov who first figured this out, the great Russian dissident. Andrei Sakharov figured out that based on what had been discovered in the laboratory, if you assume non-equilibrium processes, you don't have to know these words at all, then in the early universe, when everything was created, there would be almost an equal amount of matter and antimatter, but a little bit of excess of 1. Then what happened in the early universe, this sounds too fantastic to be true, but it's the only theory we have, is there was huge annihilation. The positrons and the antipositrons, the positrons and the electrons annihilated with each other, producing this enormous amount of energy in the form of gamma rays. And this was taking place in the early universe. There were other things like quarks and so on. We'll get into that next week. But because it wasn't exactly equal, because there was a little bit of imbalance, 1/10 of a part per million of excess of one of them, that when all the annihilation was done, there was this little bit left over. Now, we could have called ourselves antimatter, because who knows which one had more, but the one that was left over is the one we call matter. And here we are, this huge amount of energy in the universe, and this little bit of excess. Everything else was turned into energy. The little bit of excess is the matter that's left over in the universe. That sounds like science fiction, and it's not known to be true. And people are making lots of measurements in the laboratory of microscopic things to try to figure out if this really is true. But it's the best theory we have right now, as crazy as that is. Now, we're getting near the end of the hour. There are a bunch of things. This list here is an important list. There's one thing that I left off. These are things because in physicists' mind, the moon going around the Earth, that's gravity. Me being down here on the surface, that's gravity. That's all gravity. But that doesn't explain why atoms hang together. They don't hang together by gravity. They hang together by electromagnetism because they have charges on them. But that doesn't explain the nucleus. The nucleus is held together by the nuclear force, sometimes called the strong force. Not a very imaginative name. It's strong enough to overcome the repulsion, unless you put too many charges together. If you get more than 92 charges together, even the strong force isn't enough to overcome that. That's why we only have 92 elements on the periodic table. Because if you try sticking on more protons, the electromagnetic force overwhelms the strong force and it just falls apart. In fact, for some of these things like uranium, the balance is so close. The electric charge repels so much that the nucleus, the nuclear force, the strong force, just barely holds it together. In fact, for uranium-235, it'll only hold it together for about 1 billion years, and then there's a probability the thing will fly apart into spontaneous, well, actually, I'm not sure uranium-235 has them, but for some of these elements, they will fly apart, spontaneous fission. It's the positive charge overcoming the nuclear force. If you wait long enough, it's a delicate balance. But there's yet another force. We'll talk of these as the 4 forces of physics. That's alliteration, I guess. 4 forces of physics. The last force is a mysterious force that we now understand pretty well, and it goes by the name of the weak force. And the weak force is, again, really imaginative, but I think it helps you to remember what it is by the fact that it's weak. Particles in the nucleus feel the weak force. The weak force is weak. That doesn't mean it is not strong. It means it's very improbable. And what the weak force does, the place where it was discovered, is you have this nucleus like tritium that's held together, and then suddenly a neutron inside the tritium turns into a proton. Suddenly it turns, and that's the weak force. When that happens, out comes an electron, out comes the proton from the neutron that turned into a proton, and out comes a neutrino. And that's what we called radioactive decay. So I want you to know the following, that there are 4 general forces. We'll talk about unifying these forces next time. That these 4 forces are gravity, electromagnetism, the strong or nuclear force, and the weak force. That the weak force is responsible for radioactive decay. And when the weak force is involved, out comes this mysterious particle, the ghost-like particle, called the neutrino. And neutrino is a marvelous particle with marvelous properties. We'll talk more about that on Tuesday.